Okay, let's have a look at this is part two of Newton's laws, and we're going to look at Newton's third law here, and then we're going to look at setting up some problems and solving them. Okay, so Newton's third law says to every action, force, there is an equal and opposite reaction, a force. So for example, we stand on the earth and exert a force downwards, our weight force, due to gravity. Gravity is pulling us down, while the earth exerts a force back upwards. Okay, we don't just keep accelerating down towards the center of the earth pushes back to us, against us. I mean, whether you're a tennis racket, you hit a ball, tennis ball coming at you, you hit the ball, it doesn't collapse and stick to your racket. It pushes back because inside it's got air compressed inside, and when it hits, it can flex only so much and then must push back. Okay, so that's a reaction. It doesn't simply collapse onto our racket and get stuck in the strings. Okay, that's a reaction. All right, now a common situation you're going to face is setting up problems with blocks on strings, and one over the edge of the table and a pulley, and one sitting on the table. Now, what we want to do is find the acceleration for the following system. For the horizontal surface, the coefficient of friction, mu, is 0.001. Okay, I forgot to get my pen ready. All right, with all of these problems, the pulley is frictionless on the corner here. The pulley is frictionless here. The string is light so that we don't have to take into account its mass in the calculations, or at least very much smaller than the mass of the block, so it becomes negligible. The string is also inextensible, which means it can't be stretched. So if this block starts pulling the string down, the string doesn't stretch, it simply pulls this block with it, okay? Unless the frictional force can prevent it. We have to choose a positive direction, okay? So what we do is, you're free to choose it how you like. I mean, clearly looking at this situation, this is a 2 kilogram block, and this is a 10 kilogram block. Unless there's a great deal of friction here, these blocks are going to start moving down and go over the edge of the table, okay, or at least get stuck at the pulley here, but they're going to move downwards, okay. The string won't stretch, so if this block starts moving, the second block starts moving, then so will the first block, okay. But what we need to do is pick a direction. Doesn't matter which you pick, as long as you're consistent. So I'm going to pick to the right as positive and up as positive. And what you do is you apply Newton's second law. You find the net force in each of the different directions, okay? You find it in the I direction, all right? And you find it in the J direction, okay? And you do it one block at a time, okay? So for instance, on the table here, good place to start because it contains a lot of information. It's certainly, okay, now, can I just deal with the vertical? This block is sitting on the table here, okay? Its weight force is downwards, so it's m1, 2 kilograms, times the acceleration due to gravity. So its weight force is m1 times g, which is 2 times g, because m1 is 2 kilograms. So 2 times g is the downwards force. Now the block doesn't accelerate through the table. There's a reaction force, equal and opposite reaction force, and that reaction force we label R, and we have that pointing in the positive direction. You must have that because clearly the block is not accelerating into the table, okay? Just as it's not accelerating upwards off the table, okay? The reaction force is balanced, provided by the table, that is, the table pushes back and holds the block up. The reaction force is equal and opposite to the weight force. There's no net force in that direction, so we can write reaction force minus 2g is equal to 0, okay? Our friction force, and we can label that, if you like, FR for friction, the friction force. Now we're going to look in the horizontal direction. Okay, there's a tension in the string. This block here is pulling. This lower block, 10 kilogram block here, is pulling downwards. There's a net tension to the right because it wants to pull the block over the edge of the table. So there's a tension to the right, so we write plus T. But there's a friction force, and that's equal to the coefficient of friction mu times the reaction force. That's the definition of the friction force, is mu times R. and that force is in the negative direction. So we need to put minus mu times r. Okay, now all of this force on the left gives us the net force. And the net force, F net, in all of these problems, will be m times a. Now for us, for block 1, m is 2, so it's going to be 2 times a. The net force, when you've summed them all up, the net force will be the difference between the tension force and the friction force. Clearly, if this system is going to move, then the tension force is going, if it accelerates to the right, then this tension force must be greater than the friction force. So T minus mu r must end up in something that's not 0, and that thing that's not 0 is equal to the net force m times a, which in this case is 2 times a. Okay, so here's our equation in the I direction, plus T minus mu r plus T to the right, because we have plus right as a positive direction. Mu r, the friction force, is going in the negative direction, so we've got minus in front, and that's equal to the net force. And in all of these problems, always the net force is given as m times a, the mass of the object times the acceleration. Okay, from our second equation in the j direction, r, the reaction force, must be equal to 2g. So it must be equal to the weight force. In other words, this reaction force is exactly balances the weight force. Okay, so the net force in this vertical direction is 0. There's no motion in that direction now. The object's not accelerating up or down. Okay, there's no net force. Okay, now we go to the second block, and we find that in the I direction, there's nothing happening here. Okay, there's no left or right motion for the block, so in the I direction, it's just 0. Net force is 0. There's nothing. Okay, no force is acting. But in the j direction, the vertical direction, we have the tension force upwards. Okay, so that's plus T, and we have the weight force of the block downwards. And that weight force is 10g. That's the mass of the object times g, so it's 10g. And one other thing I forgot to mention, in the last video we talked about the particle model, and if you notice in this diagram here, we've got all the forces acting through the center, the geometric center of the object. Okay, so that's where all the forces are acting. So when you set these problems up, just put a little dot in the center, okay, and have all your forces, left to right, up and down, whatever your directions are, running through that center point. Okay, so they all act on that center point as though the entire mass of the block was concentrated in that center point. Okay, that's our particle model, and that allows us to set up these diagrams. So you don't have to worry about where to put forces. Is it here? Is it here? Is it there? It's none of that. Is the friction down here and this one's pulling it over the top? No, don't confuse yourself with all that. That's not the way to do it. You imagine all the mass concentrated in a single point in the center here, okay, and all the forces act through it. Okay, so just pick the geometric center and have all your forces acting through that. Okay, back to mass 2 in the vertical direction. So we have plus T up, okay, and the weight force down in the negative direction. So T minus 10g is equal to, now, net force, this object is going to move down. So the net force is going to be in the negative direction. You can see that, okay? So it has to be minus 10a, okay? Because it will go in the net direction. All right, next bit. Okay, so from equation 1, okay, which is T minus mu r is 2a. I'm going to T minus mu r equals 2a, because I'm going to take it out of sight now. Okay, so from 1, T is 2a plus 0 point, solving that, is going to be mu r plus 2a. In fact, the way I've written it here is 2a first plus mu r. Okay, so we're going to have 2a plus the 0.001 times 2g. Okay, when we tidy that up, and from equation 2 here, because the thing we don't know is the tension and the acceleration. Okay, from the second equation here for mass 2, we can write T equals minus 10a plus 10g. Okay, now these two tensions must be equal. Okay, they must be equal. the tension on the string here has to be the same as that tension there. The string doesn't stretch. It's inextensible string. It's not going to stretch. So the tension in both places must be the same. Okay, so those two are equal. So we set them equal to each other. 2a plus 0.002g is minus 10a plus 10g. Okay, let's solve that by putting the a's together. So take this over the other side, minus 12a. This 10g bring over here, plus that. This, when we calculate that, or approximately rounded off, will give us this negative value here. Minus 10g is much greater than this. Gives us this value here, divided by the negative 12 there. We'll get an acceleration of 8.165 meters per second. Okay, that is our acceleration. Now, how do we interpret that? Well, the acceleration is going to be down, okay, because we know the system goes to the right here, okay. In this direction, acceleration is positive, in this direction it's negative. We have to interpret the problem, it is going to be negative, okay. Now, this would have, this still would have come out, had we not put minus here because we didn't know which way the system was going to go, it would have come up with a negative answer, would have told us down, okay, but as it was, I've said, well, from the beginning, we know it's going to accelerate down, so we'll put minus there straight away. Okay, notice the friction force Fr is mu times r. Okay, so our acceleration is 8.165 meters per second, and it's going to be in the downward direction. Okay, so this is the magnitude of the acceleration. We add, since this block is going to accelerate that way, so will this one. Okay, both are going to have the same acceleration because the string can't stretch. All right, that's it.